Ever need to check if a network is robust, fully connected, and loop-free? Graph Valid Tree is a Pattern Mastery 100 favorite, used by Google, Apple, and Meta to test your core understanding of graph cycles and connectivity. Over 30% of candidates get tripped up on edge cases like cycles or disconnected graphs. Master this and you'll breeze through network design and validation problems. Let's break down Graph Valid Tree with a basic method, ensuring you can confidently tackle any connectivity or acyclicity question in interviews. Given n nodes labeled 0 to n1 and a list of undirected edges, determine if these edges form a valid tree. A valid tree is connected. There's a path between every pair of nodes. Acyclic, no cycles. Integer n, number of nodes, list of undirected edges. Boolean, true if the graph forms a valid tree, false otherwise. Imagine verifying a computer network or electrical grid, no redundant paths, cycles, but every device must be connected. An interviewer might ask, how would you validate that a topology is a tree and not a forest or a cycle? What's tricky? Must check both connectedness and absence of cycles. Some solutions miss edge cases, disconnected graphs, or graphs with exactly one cycle. For a tree, exactly n1 edges for n nodes. Edge count check, if there aren't exactly n1 edges, it can't be a tree. Connectedness check, use DFS/BFS to visit all nodes from node 0. If you visit all nodes, count equals n, the graph is connected. If any node is unreachable, it's disconnected. Cycle check, if any edge leads back to a previously visited node, not the parent, it's a cycle. Edge count shortcut, if the edge count is correct and you visit all nodes without cycles, it must be a tree. Let's clarify. Using Union-Find, disjoint set union, DSU, is also common. Detects cycles as you add edges and checks if all nodes are ultimately connected. Edge cases. Disconnected components, not a tree. Extra edges, more than n1, must have a cycle. Single node, n equals 1, edges equals 0, valid tree. Edge count, return false if len edges, equals n1, DFS/BFS. Build adjacency list from edges. Start from node 0, mark nodes as visited. If during traversal, revisit a node that's not the parent, it's a cycle, return false. After traversal, check if all nodes are visited, connected. Return true if no cycles and all nodes visited. Let's walk through this solution. The main goal here is simple. Determine if a graph forms a valid tree. If the graph has the wrong number of edges or isn't fully connected, it fails the tree definition. If it has exactly n1 edges and BFS reaches all nodes, everything works smoothly. Approach. BFS plus edge check, ON plus E. Time complexity, ON plus E. Begins the method that decides if the graph is a valid tree. A tree must have exactly n1 edges, fail immediately if not. Creates an adjacency list to store graph connections. Initializes a list for each node. Builds the undirected graph by adding both directions. Tracks which nodes have been visited. Queue for BFS traversal. Start BFS from node 0 and mark it visited. Counts how many nodes we successfully visit. Begins BFS until no more nodes are reachable. Processes a node and increments the visited count. Explores all neighbors of the current node. Visits unvisited neighbors and adds them to the BFS queue. Ends neighbor loop. Ends BFS loop. If BFS reached all nodes, the graph is connected and a valid tree. Ends method. And that's how the algorithm works. Efficient, simple, and elegant. Now let's verify the solution using the provided test case. This input describes a graph with 5 nodes and 4 edges. It matters because for a valid tree, the graph must have exactly n1 edges and be fully connected. Short reasoning. The algorithm first checks edge count, 4 equals 5 to 1, so it passes. Then BFS starts at node 0, exploring all connected nodes. It reaches 1, 2, 3, and finally 4. All 5 nodes are visited, meaning the graph is connected with no cycles. This makes perfect sense because the graph forms one connected component and satisfies the tree edge rule, so it is indeed a valid tree. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's walk through this solution. The main goal here is simple. Check if an undirected graph is a valid tree using Union-Find. If we ever create a cycle or the edge count is wrong, it's not a tree. If we connect all nodes without forming cycles, everything works smoothly. Approach: Union-Find, disjoint set, ON time complexity, ON. Starts the method that decides whether the graph is a valid tree. Quick tree check: a valid tree with n nodes must have exactly n(1) edges. Array to track each node's parent in the Union-Find structure. Array to track tree height to help union by rank. Initially, each node is its own parent. Each node starts as its own set. Loops through every edge in the graph. Attempts to union the two endpoints. If it fails, a cycle was found. Immediately returns false if adding this edge creates a cycle. If all edges were added without cycles, the graph is a valid tree. Starts the find method to locate the root representative of x. While x is not its own parent, keep climbing up the tree. Performs path compression to shorten the path to the root. Moves x up one step toward the root. Ends the loop once the root is reached. Returns the root representative of the set. Starts the union method to merge the sets of x and y. Finds the roots, representatives, of x and y. If they already share the same root, adding this edge creates a cycle. Attaches the smaller rank tree under the larger rank tree. If Rx has higher rank, attach y under Rx. If both ranks are equal, pick one as new root and increase its rank. Makes Rx the parent of y. Increments the rank of Rx since its tree got taller. Ends the equal rank handling block. Returns true to indicate the union was successful. No cycle. Ends the union method. Ends the solution class. And that's how the algorithm works. Efficient, simple, and elegant. Now let's verify how this behaves on the given test case. This input defines 5 nodes and 5 edges. It matters because a valid tree with 5 nodes must have 4 edges and no cycles. Here we already see n(1 equals 4), but we actually have 5 edges, a red flag. Short reasoning of how the algorithm processes the input and what it checks for. First, edges.length equals n(1) evaluates as 5 equals 4, which is true, so the method immediately returns false without even running Union-Find, because the edge count alone disqualifies it as a tree. This output makes sense. A graph with 5 nodes and 5 edges cannot be a tree. It must contain at least one cycle, so returning false correctly reflects that it is not a valid tree. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's have a quick recap. We're given n nodes and a list of undirected edges. The task is to decide whether these edges form a valid tree, meaning the graph is both connected, every node reachable, and acyclic, no loops. If it passes both, it's a tree. If not, it's just a network with issues. The tricky part? Balancing two conditions at once, ensuring all nodes are connected without accidentally introducing cycles. Many candidates forget the edge rule. A valid tree must have exactly n(1) edges. From there, the challenge becomes verifying that all nodes can be reached and that no back edge creates a loop. Here's how we planned it. Edge count check. If edges does not equal n(1), return false immediately. Build adjacency list. Represent all node connections. DFS or BFS traversal. Start from node 0, visiting neighbors while skipping the parent node. Cycle detection and connectivity. If we revisit a node that isn't the parent, it's a cycle. After traversal, if we visited all nodes, the graph is connected and valid. We implemented the traversal, marked visited nodes, and avoided false cycle triggers by tracking parents. The logic executed smoothly, and the solution ran successfully on LeetCode without any errors. We validated against multiple scenarios, perfect trees, disconnected graphs, and cyclic ones. Every test case passed, confirming that the algorithm correctly identifies valid trees. The takeaway? Every tree problem is a lesson in structure. One path between any 2 points, no more, no less. Once you can balance connectivity with acyclicity, you'll have mastered one of the most universal principles in graph theory and system design.